Hello, everybody. Thanks for joining us for this discussion. My name is Paul Hillman, and we're here with my colleague Fred.
Hi, guys.
And today we're going to talk a bit about PWI, or plane wave imaging, and how it can be beneficial for different applications. A little bit of the agenda today. Here we are. So we'll introduce what PWI is, some of its benefits. We have some examples with real data captured with PWI method compared to others as well. At the end, a little bit of updates on what's coming from some of our software, and some time at the end for questions. So if you're watching this live, please feel free to write your questions in the comments box, and hopefully get to them at the end, or feel free to send us the questions as well, and we'll cover those. So a little bit about what PWI is, and we'll start here from FMC, full matrix capture. Everybody knows beamforming phased array. In recent years, full matrix capture based methods have been more widely adopted, and full matrix capture is where we take a phased array multi-element probe and we acquire data from elemental A scans. So we would fire each individual element sequentially, and store an A scan for each receiver element as well. So taking a typical example of a 64 element probe, we would fire element 1, listen on 64 elements, save an A scan for each one of those, then fire element 2, listen on 64, and we end up for each probe position having 64 squared A scans in full matrix capture for that 64 element probe. So it's 4,096 A scans. So from that data, we can process that to do advanced imaging or optimally focused imaging, either live, so during acquisition on the fly, or in post-process data as well. So the difference with plane wave imaging from full matrix capture is, instead of firing individual elements like FMC, we will fire a beamforming aperture. So we might typically fire all elements of the probe at once to create a beam that can be steered to the desired angle that we want, and focus. But typically we do this unfocused, so we get nice wide beams with lots of energy into the component. And depending on the application, you choose the number of beams that would be needed to cover the area of interest. A typical weld example might be 7 beams in emission from 40 to 70 degrees. And for each one of those beams in emission, we will again store elemental A scans. So for each pulse, we're going to store 64 A scans. But now we have 7 times 64 A scans rather than 64 times 64. So we have the data file size is much smaller, and the demand on processing is much smaller. And also the main point is the firing cycle is much shorter as well. We're only firing 7 times. We don't have to wait to fire 64 times. So one of the major advantages of PWI is the speed that we can inspect at. And this slide just shows you a little bit about how that looks. So on the right, you'll see that animation is showing me 7 beams, one at 40 degrees, one at 45 degrees. We're going to do one every 5 degrees up to the top of the 70-degree beam. And the idea is, like any weld inspection, to make sure we have beams covering the region of interest, and that we have significant overlap of those beams coming, so we have good sensitivity as well. And you can see at the bottom picture there the overlapping beam simulations from each one of those beams. And then what do we do with that raw data that we get, the PWI data? We do TFM reconstruction. So just like TFM we gather from FMC, we can apply the same sort of algorithms, the total focusing method, to the raw PWI data, either live, so during scanning, or after the fact. And with TFM, we take the area of interest, we define a region we're going to look at, and we decide how many pixels we're going to use to reconstruct that region. And that's really based on the size of the frame, the frequency of the probe we're using, and a value called amplitude fidelity, the sensitivity we want to get, and the chance of hitting the real peak amplitude that we want. So we take each pixel and we take the raw data and we apply delays to each pulsar receiver pair so that we obtain the amplitude at that point, considering the beam path that we wanted to reconstruct with. So how did the beams get there? Was it the direct path, or was it skipping off the back wall? So the benefits of TFM, many people will know this now. We have ideally focused signals everywhere within our region of interest, within the physical limits that we have. So within the near field of the beam, and within the steering capability of the probe and wedge combination. So we have excellent image resolution and to get better characterization and sizing of challenging floors. And the benefits of PWI data acquisition, there's several of them compared to FMC. The emitted pulse from the full aperture has more energy and is more directional than a single element excitation. It provides greater sensitivity and better signal to noise, together with higher PRF, high scanning speeds, because of significantly shorter firing sequences and less elementary signals to process. At the same time, the less elemental A scans we have means significantly smaller data file sizes for raw data saving, meaning that it becomes more practical to do raw PWI data saving for offline processing, which has some other benefits depending upon the application. So we come to a few examples to show you of what PWI data looks like and how we can use it. An example I did yesterday with some of my colleagues in Swansea, using the Topaz 64, we acquired PWI data using the link scanner there. You can see from Eddyfi, that one is the high temperature scanner, the high temperature version of the link scanner. We have two G3 phased array probes, so 64 element 5 megahertz probes either side of the weld, and they're both doing PWI and TFM reconstruction. At the same time as that, we're running simultaneously TOFT, and this TOFT we're using here are Ionics high temperature TOFT probes. They typically work from ambient to 350 C, but we're using it at ambient temperature here. On a pipe sample we have there, which has some admittedly rather large gouges inside that pipe in the weld volume, which is repaired over, and you can clearly see them in the data as well. You can see the video of this acquisition here. We're going about 100 millimeters per second, doing all of those groups at the same time. It is possible to do more TFM reconstructions with the Topaz. We could do up to 8 TFM reconstructions at once, coming from TWI to PWI channels at the same time as other methods, which could be phased array, which could be TOF, depending upon the type of application you want. But pretty reasonably fast scan speeds with a good balance there of data throughput and data quality as well. And I'll just zoom in a little bit on the data display. You can see at the bottom there. And they're volumetric views, they're projected views. So the sector views you can see in the top left and top right, coming from the 90 and 270 SKUs, are the full volume of the weld. You're seeing the floors coming from the full volume, as well as the same on the C scans and B scans that are at the bottom. The top data is obviously very clear where those indications are. Also pretty obvious in the 3D view too. Just taking something that's a bit more realistic as a floor, this is a cluster of porosity I looked at with FMC TFM, so live FMC TFM, as well as phased array UT. This is optimally focused phased array, I should say. So I did a focusing here right in the center line of the weld. So we have a very nice image with phased array UT. That one's using 31 beams, so typical 1 degree resolution between 40 and 70. But just a note, if my focusing wasn't optimal at that point, that's the downside of phased array, that if my focusing was somewhere else on the fusion face, for example, then I might not clearly see that porosity as nicely as I do there. With TFM, of course, the idea is that we're focused everywhere within the region of interest, and we get very nice clarity of image and detection of the cluster of porosity on that image on the left-hand side. On the right is the same data, but now acquired with plane wave imaging TFM. So I'm using the same TFM reconstruction, but my firing sequence is using plane wave imaging. I have a lot more energy in there, and we're in fact able to resolve a couple of those pores a little bit better than the live FMC TFM, thanks to the increased energy. And the big difference here comes in the scan speed. So I've represented that at the bottom with the live FMC TFM, taking that as the base speed. If that's 1 times, the phased array would typically be about twice as fast as that. And the live PWI were about 4.5 times faster with that setup with the PWI than with the FMC type acquisition. So we can go a lot quicker. Something else quickly I did is just to show the raw PWI data reconstructed with some of the offline algorithms we have available in Ultravision. One is PCF, that's phase coherence factor, you see on the left. And that's an algorithm we use to construct the image which weights the in-phase information, so how well in phase the A-scan signals are at that particular point, with the amplitude information. So it's a combination of both. It significantly reduces the background noise. You get excellent resolution on that porosity there as well. And on the right as well, another algorithm, delay, multiply, and sum, where there's a multiplication step in the TFM computation before we do the addition, which again reduces the background noise significantly and gives us excellent SNR on that porosity, as an example. And now over to you, Fred.
Thanks, Paul. So I think that Paul showed that the main advantage of PWI obviously is the scanning speed, a big improvement. But another one is the improvement of sensitivity as we fire like all the elements very often. So we send more energy into the parts. And one application we're going to look at now is HTHA inspection, so high temperature hydrogen attack, using PCI, so phase coherence imaging, which is a new way of processing the FMT data or the PW data. The application here is you can see a cross-section of the HTHA sample, and you can see the size of the micro cracks. So like the sample we looked at is few microns to 100 microns cracks, so really, really tiny. We designed a probe, 64 element, 10 meg, with a focus in the passive plane. You can kind of see the beam field here in the passive plane. So on the left side is the size of the focal beam. On the left side is the depth. And you can see that the probe was designed to be below 3 millimeter in the passive plane, between 4 millimeter in depth, all the way to 35 millimeter. So really the probe was designed to look at this depth. Next slide, please. Paul, next slide. Thanks. So phase coherence imaging, we did a blog and a coffee break, so I'm just putting the link at the bottom, so I'm not going to spend too much time on phase coherence imaging. But essentially, this is the same as TFM, except instead of using the amplitude of the FMC or PWI data, we use the phase or the sine function, which is a little bit easier to use on the system. And we performed the same calculation as a TFM, except that we obtain an image in phase. Typically on the PCA image, you have a better sensitivity on tip diffraction on very small indicators, and you tend to erase the indication on back wall, front surface, and so on. So obviously HTHA having all these small cracks has all these small diffractors, so it's a perfect application for phase coherence imaging. So next slide. All right, so the first thing we did obviously is to compare TFM to full TFM to PCI data, both acquired with a full matrix capture. So we have the TFM on the left, we have the PCI on the right with a dedicated color palette. And you can see on the TFM image, we have some artifacts, which are very typical when we do L0 inspection with TFM. This artifact really depends on your pitch, on the thickness of the component, but you can see these arcs, and they go all the way to the back wall. And if you have very tiny indications like HTHA, it's going to be very, very difficult to detect any HTHA due to this artifact. And these artifacts are caused by the back wall. So if you look at the C-scan at the bottom, you only see like these large indicators, which are probably more inclusions. If you look on the right-hand side, you see on the PCI image that you don't have any front surface echo. The back wall echo is pretty much gone except in the middle. and you have this artifact argon, which allows you to see these very tiny small indicators, but they're still like pretty small. So if we go to the next slide, what we did is we used plane wave imaging. Again, plane wave imaging is going to send a lot more energy into the part. So for this application, we did 20 angles between -20 and +20 degrees, so every 2 degrees, firing the full 64 element. And we calculated exactly the same PCI image. So you have the PCI from the FMC on the left, and you have the PCI from the PWI on the right, both using the same color palette. And you can see kind of a big increase in terms of PCI image contrast. I don't want to say amplitude because it's a phase, but you can clearly see the cluster of HTHA that you can kind of notice on the left, but it is a little bit more difficult. And the main reason is even though PCI is not based on amplitude, you still need to be able to extract a phase on each of the FMC data. So if the signal-to-noise ratio is close to 0, which is the case in many of the FMC data on the left, because the defects are really small, then you are not going to be able to extract a phase. So you have a very few elements that contributes to the FMC, to the PCI image. On the right side, because you send a lot more energy, you are able to get a little bit of signal-to-noise ratio on the plane wave imaging data set, so you can extract a phase. And this way, when you calculate PCI image, you have a much better contrast again. You could also average, but the problem of averaging, obviously, is it's going to be a big drop in scanning speed. So here with plane wave imaging, we don't have to average. We can go a lot faster compared to FMC, and we have a big increase of sensitivity. Next slide. Well, that's exactly what I just said. I guess I was ahead of the slide. But in this case, we use about 20 angles compared to 64. So we had an increase in speed of about 3.5-4 compared to FMC. So you can really do your HTHA data at a nice scanning speed. So you don't have to go really slowly with the FMC. All right, thanks. Next one. All right, another application also for sensitivity is HDPE, so high density polyethylene pipe that we see a lot in more and more. We see because they don't have corrosion issues and they can be cheaper compared to carbon steel piping. However, for UT inspection, because they are this very attenuative material, we cannot use shear waves. They just don't propagate at all, at least in the frequencies that we are using typically in NDT. And even L waves are deeply attenuated. So I gave you a range here, but that might be different on a different HDPE pipe, but between 0.3 and 0.5 dB per millimeter at 2.25. So the part we are looking at right now is about, we say 30 millimeters or 35, I believe. We looked at some defects. You can see like some tiny saddlery holes along the fusion face. And we also put a notch on at the bottom. So we want to see if we are able to detect the tip diffraction. Next slide.
It's going.
Yeah, thanks. So we compared FMC, the full FMC, so firing the 64 element, to plane wave imaging. I forgot to mention here I'm using a probe at 2 megahertz. It's actually a probe at 5 that I'm driving at 2 megahertz. Because like with the bipolar pulses of either the Topaz or the Gekko, you have pretty good capabilities of exciting probe out of frequency. You can see the plane wave imaging on the top and the FMC at the bottom, and you can see the echo dynamic on the left. So you can see the 3D effects, and you can clearly see that the FMC data, you can clearly see the electric noise. Because we are only firing one element at a time, the elements are tiny. It's a pitch of 0.6 millimeter, a very typical pitch. We don't send a lot of energy every time we are firing, so we are close. We have a signal-to-noise ratio. I think if you click next, again, one more. Yeah, here you go. You can see at the hole at the bottom with FMC we have a signal-to-noise ratio of about 8 dB, which is kind of still sufficient, but it starts to get really small. And we have about 21 dB using plane wave imaging. Just by firing all the elements at the same time, we are able to get much better signal-to-noise ratio. So when you have these tiny defects, you're going to be sure that this is a defect and not another indication. Next slide. Okay, so now we looked at the notch, and we want to see if we are able to detect the tip diffraction. Again, same FMC, same plane wave imaging. You can kind of see the corner echo at the bottom of the weld, and you can see the tip diffraction. On the FMC data, we have only about 5 dB of signal-to-noise ratio. You can really see increase the gain, the soft gain at the bottom. So we have our tip diffraction echo at 80% screen height, and you can really see the noise, the electric noise up. So that's why we only have a signal-to-noise ratio of 5 dB. For plane wave imaging, we improved the signal-to-noise ratio about 12 dB, actually even 13. It's hard to see here, but we have about 17.7 dB of signal-to-noise ratio in plane wave imaging. So really, when you do your scanning with plane wave imaging on HDPE piping, you're going to focus across the entire depth. So you're going to have very high spatial resolution. And at the same time, you're going to have enough energy to have sufficient sensitivity to detect tip diffraction. For example, if you have a lack of fusion and you want to size a lack of fusion along the fusion face. Next slide. I think it's you after. Yeah. Okay. There you go.
That's what you're describing. Yeah. So.
Yeah. Exactly.
Yeah. No. Great results on the HDPE there. I think really strong improvement on SNR. Good to see that. Okay. Just to mention, some updates are coming soon. We're going to be launching a new version of UltraVision shortly, 3.12 R9. This is adding some additional features for those using UltraVision. We have live TFM and plane wave imaging with up to 2 64-element DMA probes. So we can use PWI and FMC TFM on dual matrix arrays, large ones, with some excellent results as well. Similar improvements to SNR that you see on that challenging application Fred just described. There was a presentation, a coffee break we did recently on austenitics and dissimilar metal welds using DMAs, which shows some very good results, improved SNR with PWI methods. And we've, in the background in UltraVision, some optimized FMC PWI raw data recording. So this is just to improve the speed and efficiency at which we save raw FMC or PWI data to increase the speed and throughput if somebody is using that. And some welcome new smoothing algorithms as well for phased array UT imaging. Those used to using the Topaz or UltraVision may be familiar with the images like that of the porosity on the left. It's a particularly bad case I've shown, but the new smoothing images available, filters available, which will be available in your view properties. You will be able to have lovely smooth images like you see on the right there. So it'll be available for anybody to download for their Topaz, Topaz 32, 16, or 64, and as well as UltraVision classic versions as well very shortly. Anything, Fred, you want to mention about Capture?
Yeah, so Capture 4.1, which I use for PCI, so we already presented PCI, is probably coming at the end of first quarter, maybe beginning of April. We'll see with the testing. I just don't want to mention yet all the development we're going to have, but obviously phase coherence imaging is going to be one of the big developments among others. So there will be like some nice features. So end of first quarter for Capture 4.1 for Mantis and Gekko.
Great. Looking forward to that one and trying that as well myself on the Gekko. So that's the end of our presentation. It's time for questions.
So you want to answer this one, Paul?
Yeah, sure. Okay. Which systems can use PWI? So the portable platforms from Eddyfi that can use PWI today is the Gekko and the Topaz 64, both available with PWI. And the RDAU, the remote data acquisition units, are the Panther and the Emerald, all run on PWI. So it's available to use today.
Okay, so what is the recommended pitch size for PWI to avoid spatial aliasing, so grating lobes? I would say exactly the same as phased array or FMC. So we typically use the same probes, so 0.6 millimeter pitch for 5 gigahertz. So nothing particular. You just have to respect this the same pitch as a PUT to avoid having these grating lobes.
I'll take this one. Yeah, how do you select the angles needed? So as shown a bit earlier in the coverage map, the beam simulation and the ray tracing, the idea is just like phased array, really, to ensure you have, if you're doing weld inspection, we'll take as a typical example, to ensure we have the beams covering the areas of interest, so over the root and up to the cap, with some additional for the heat affected zone, and ideally with the right angles hitting the areas that you want. And the number of angles you need will be based on the angular resolution. So we could do some beam simulation to see what the coverages are like and what the amplitude plot is like for each of those beams. That's available on the instruments as well, on the UltraVision instruments, to see your simulation of that. So you want to ensure good coverage, good overlap of the emission beams and in the areas of interest.
Yeah, and yeah, typically for the number of angles, if you want to increase sensitivity, you're going to add more angles, but you will have a drop in scanning speed. So you have to find the right compromise for your application. So is PWI code compliant? It is. Actually, if you look at ASME, which was section 5, which was revised back in 2019, they have a more general definition for FMC. We tend to think of FMC as firing the element one by one. In ASME, they actually call that elementary FMC. And for ASME, FMC is just like you can fire any group of elements, any aperture with or without delay loss, and this is the same for reception. So ASME is really, really general in terms of what you can do. As long as you record the elementary data to do your TFM after, you can do pretty much anything in terms of acquisition. All right.
That's the end. Thanks everybody for watching, and thank you, Fred, for the collaboration.
Yeah, it was nice.
Yeah, let's do it again. Any questions, feel free to send us, and see you all soon. Thanks.
Bye, guys.